All right, so chapter 6, here we are. So chapter 6, we begin to work with inverse trigonometric functions. So this will be like inverse sine, inverse cosine. We did have this notation and this idea introduced a little bit earlier, quite a bit earlier in the class, but just as something to type on a calculator, not something to use in an algebraic way. So what we're going to do in chapter 6 here is introduce both graphically, definitionally, and for the purpose of using algebraically to solve equations, we're going to introduce all 6 inverse trigonometric functions. And then we're going to start using those to solve equations with trig functions in them and things like that. So the idea of an inverse function is a big idea. For example, each operation has an inverse operation. Adding 5, the inverse of that is subtracting 5. Squaring something, if you restrict that function a little bit, the inverse is square rooting something. So the idea of inverse functions, one-to-one functions which have an inverse, things like that, those topics are introduced in algebra, usually in algebra 2. And so the first 8 slides of our PowerPoint today focus on a review of what it means to have an inverse function and how you get it and things like that. So I have a previous video which I shot and posted covering the review of, in general, what it is to be an inverse function and how we obtain one. And so as I'm now going to skip over that and pick up from where that last video left off to start in the next phase of this discussion for inverse of a trig function. So as we go forward here, we're going to see this first section of chapter 6. The inverse functions part, which I've underlined here, is on the first video. And then today, or in this video, we're going to now try to talk about specifically the inverse sine function, inverse cosine function, inverse tangent function, and other inverse circular functions. Then I'm going to probably save the last part about inverse function values and some problems they do around that are a little complicated. We won't probably be able to get to that today. So that's the plan for this video. And so I'm now going to scan back over the slides that I went over in detail with on the last video. And as you can see, I did a lot of stuff in the last video. So if you haven't had a chance to take a look at that, all of this mess might be intelligible. But there was a basic general introduction to the idea of inverse functions, definitions, et cetera, et cetera. So what I'd like to do now is go to this blank graph that I set up to begin our discussion today about trying to produce an inverse of a trigonometric function, and specifically the inverse sine function. So here's where we will begin. And so let's say we're going to call f of x the name for our sine x function. And so what we want to do is create the inverse of the sine x function. And just to remind ourselves that this -1 is not an exponent when you're using it in the context of this f function with a -1 superscript there. That means the inverse of the f function. And we've used this already because the way we write this for the sine function is we write sine and we put a little -1 up here of x, and that's the inverse function of the sine function, or the inverse sine function, sometimes referred to as the arc sine. So this might also be written as arc sine of x. So there's a couple of times we've just punched these on a calculator in some previous problems, but we want to talk more in general about this now and look at it graphically and how it's created and what it does. So as we reviewed in the last video, when you have an original function and then you come up with or create or define an inverse for that function, you have an exchange in the x and the y variable, an exchange in the domain and the range. So if I have my f of x function over here, and we imagine having a table of values for that. Then the x values are the domain values. And the answer you get from the sine function are the range values. And when we're thinking about the sine x function, like in a radian measurement or in an angular measurement, either way, what you plug into the sine function are angles. And so to keep that in mind, initially, let's say we write these out in radian format, but remind ourselves what the angles are. So I can plug in a 0 for x, and that could be 0 radians or 0 degrees. And when I evaluate sine of 0, I also get 0. And that means I get the origin as one spot on my graph of sine. And just to put down some of our key things, if I go over to like pi over, I'll just do pi over 2. If I go to pi over 2, actually, we'll go ahead and do a little bit better. Pi over 4, if I go to pi over 4, then I get square root of 2 over 2. When I go over to pi over 2, that's equivalent to 90 degrees, and that's when the sine becomes a 1. And so on this graph here, I've scaled it a little bit close to normal. Pi is normally like 3.14. I put that at around the 3rd mark there. So the scale is a little bit shorter, but still pi over 2 would be in the middle here. And if I have this as a height of 1 on my scale of my graph, just to sort of have these match, then when I'm at pi over 2, I'm all the way up at 1. That's the top of the bump of the sine function. When I'm at pi over 2, I'm somewhere down here. And I have this kind of curve that comes up and goes over and then falls back down to 0 as I get over to pi. So if I go to pi, I get to 0. And then similarly at 3 pi over 2, which is sort of the borderline between quadrants 2 and 3, the y value is at -1. So that's when I get down to the bottom of the sine function. And then, of course, as I complete one period of the sine function, as I complete one period of the sine function, I end up back at 2 pi and back at 0. And the thing also to remember, of course, is that this just continues in both directions. Do that a little bit quicker and sloppier. All right, so we have this basic sine graph, and we can think of the tables of values that get it. The question then becomes, what would we have to do to have an inverse of this function? So the first thing I would point out, as when trying to think about whether any function's graph that you're looking at is invertible, is does it pass a horizontal line test? The horizontal line test is, again, how we determine whether a graph's function is 1-to-1 and therefore whether it has an inverse. Well, we can see pretty quickly that lots of horizontal lines that I might draw across this graph would cause it to fail the horizontal line test because it contacts the graph in multiple places, in fact, infinitely many places. So the sine function is not 1-to-1, just like the x squared function is not 1-to-1. And just like with the x squared function, the way we can produce an inverse to the sine function that in its full glory does not have an inverse is we can restrict the domain. We can limit the parts of the graph that we're considering until it does pass the horizontal line test. We would have to take away a whole lot of the sine function. So just as a reminder, in the case of the x squared function, which had this crazy big picture, and I did a bunch of stuff to it above, we ended up taking away the left arm of the parabola and just using the right arm so that we could then have it pass the horizontal line test and create an inverse. But here we need to take away a lot of the sine function in order to have a chance to have horizontal lines only hit the graph once. So let's look at how we want to accomplish that. So let's first point out that for the sine function, the domain of the sine function is you can plug in any angle you want in radian measurement. So the domain is all real numbers, which has this R symbol for R real numbers. But the kind of answers you get from the sine function, the range of the sine function, is just anything between -1 and +1. And so we can see that all of these values in the right Y column, the range column, are always going to be numbers on the interval from -1 to 1. So if we are restricting the domain, we're not going to allow all real numbers to be considered as angle measurements for X. We're going to restrict which real numbers we allow to be plugged in. We're going to restrict the domain so that we eliminate part of this graph. But we still want to make sure that all of the range values are produced in the part of the graph that we leave here. And so it turns out that the way they choose to do that as a default is that you start on the left here, where X is equal to -π/2. When X is equal to -π/2, and I'll put that over here, just so we have it on our table. When X is -π/2, the Y value for sine is -1 there. And if I move over 2π from there, it would be at 3π/2. It's also -1 again there. It's a -1 lots of places. But we're going to begin thinking about having a -1 value in the range attained when X is -2. And then if we move to the right from there over to when X was +π/2, whoops, let's do that color coordinated. If I then move over to when X is +π/2 here, then we see that the sine function has gone from -1 at -π/2 all the way up to +1 at +π/2. In that limited set of input values between -π/2 and +π/2, we will now see that the sine function has covered all possible output values that it can ever attain. -1, 0, 1, and everything in between. The entire range is covered in those angle input values. And if we also just look at that part of the graph, what you will see is that that little piece of the graph now passes the horizontal line test. And so what we are going to do is to create an inverse for the sine function. We are going to eliminate everything outside of that range. We're not going to consider any of those values. We're going to restrict the domain of the sine function and only go between -π/2 to +π/2. If I make that restriction, then I get just this little segment in the middle, which I'll overdraw with red so we can see it. We get just this graph. This is still the sine function, but it's only the part of the sine function produced from the restricted domain from -π/2 to +π/2 for X. And if I just focus on that part of the sine function, we will see that actually now it passes the horizontal line test. It now passes the horizontal line test. So we're going to take that part of the sine function, that modified sine function with a restricted domain, and we're going to use that to create an inverse. We're going to use that to create an inverse. So the thing to remember about an inverse is that when we make this inverse, let's say I use blue for that, that for the inverse, the domain of the inverse is the range of the original function, and the range of the inverse is the domain of the original function, because we're switching all the X and Y values. And so now the domain of our inverse function will be from -1 to 1. And the range of our inverse function, because we restricted the range to make it work, will now go from negative pi over 2 to positive pi over 2. And the thing to also take note of to help us realize that these things have been switched is that the domain is now a number that we would normally think of, whereas the range is now an angle. Because for the original function sine, we plugged in an angle and we got a number. So for the inverse, excuse me, for the inverse function, we'll plug in the number that we would have gotten and it will spit back out the angle that we would have started with. And in terms of what this would look like, again, the idea is when you switch to the inverse, you reflect the graph around the line y equals x, the 45-degree angle or diagonal line. And in this case, a lot of this graph is kind of close to that line. If I draw the line goes through these points 1, 1, 2, 2, 3, 3. There's the diagonal line. So there's the line y equals x. And so I'm basically going to flip that little red part of the sine graph around or reflected around that line. And when I do that, maybe I'll try that in orange, see if that helps. Then the point pi over 2, 1 gets flipped up here and becomes the point 1 pi over 2. I switch the x and the y value. So pi over 2 gives you 1 for the original sine function. So for the inverse sine function, if I plug in the 1, I get pi over 2. 0 still gives me 0. On the original function, when I plugged in pi over 4, I got root 2 over 2. So now when I plug in the square root of 2 over 2, I get pi over 4. Going down the list, I could get more of these, but let's look at the last one that we finished with, because at least I can even see it on the graph a little bit. If I take negative pi over 2, negative 1 on the original sine function, that gets reflected across the diagonal line and moves over there. And that means that when I plug in a negative 1, the output of the inverse function will be negative pi over 2. And I can kind of connect all of these points in between. So it's a reflection. And of course, this graph is not going to be accurate at all. And they will give you much better graphs. But just to show you the idea of what's going on, let me take out that little line that I drew across there. And I get this graph instead. All right, so this sort of orange curve I have in here is just a flipped version of a piece of the sine function, but that is in its entirety the inverse sine function's graph. And you can imagine that there's a table of values where you plug in x and inverse sine of x. And the idea is that the domain and the range have been switched, the x and y's have been switched from the sine function. So for the inverse sine function, I plug in numbers between 1 and negative 1. And it spits out angles between negative pi over 2 and positive pi over 2 that I would have used in the sine function to get that number. So that's a lot. It depends on you kind of having an idea already of how inverse functions work, what's going on with them graphically. That's what I tried to discuss in the previous video. But all of that work in the previous video puts us in a position to try to see how we can take the sine function, which in its entirety does not have an inverse function because it fails the horizontal line test miserably, but that if we restrict the domain of the sine function And we just talked about how to do that. We're going to restrict it down to negative pi over 2 to positive pi over 2. And if we take that little piece and we can then pass the horizontal line test, we can use that to create the inverse sine function by reflecting that around the line y equals x and exchanging all the x and the y values of all the points on that little restricted part of the graph. All right, so what we end up with is a function. It's on your calculator, it's on Desmos, it's on pretty much any calculator that has a trig function. We'll also have inverse sine on it. And what it does is it takes values from sine that were answers before, that were in the range between -1 and 1, and it spits back the angle between negative pi over 2 and pi over 2 that would have produced that. And so I have a little table of values here, but you could imagine plugging in other things as well. So let's say, for example, that I input into the inverse sine function a different kind of value you would get, like 1/2. 1/2 is a value that we can get from the sine function. So what this means is if I'm trying to evaluate sine inverse of 1/2, we are basically asking ourselves, what theta value would that be? What angle would you need to get 1/2 in the sine function? Meaning, what theta has sine of theta equal 1/2? And when we are trying to answer that question, the theta value we choose has to be between negative pi over 2 and positive pi over 2, because that's where we restricted the angle measurements in the original sine function to produce an inverse. So what theta between negative pi over 2 and pi over 2 would we use in the sine function to get 1/2? You could imagine that graphically trying to look that up. You may recall from our tables of values for sine function that the sine function gives you a 1/2 value, a y value on the unit circle of 1/2 when you're at an angle of pi over 6 in the first quadrant. So these will always be first and fourth quadrant values. Negative pi over 2, 0 to negative pi over 2 is fourth quadrant, 0 to positive pi over 2 is first quadrant. So this would mean that if I plug 1/2 into the inverse sine function, it comes back with the pi over 6 angle as its answer. If I plug in square root of 3 over 2, well, that would be the angle in quadrant 1 where the y value of the point was square root of 3 over 2, which is pi over 3. If I plug in like negative root 2 over 2, so that's the angle where the y value is negative root 2 over 2, it would need to be the angle between negative pi over 2 and 0, which is in quadrant 4, and that angle is negative pi over 4. So there's a lot here. This was a big discussion, riding a bit on the back of the previous video's discussion that I shot, but we're going to do all of this for all 6 trigonometric functions. And again, keep in mind, you're taking the x, y points from the original trig function, even if you limited it, and you basically flip the y and the x, as we were seeing with these tables of values. All right, so that's my overview with my attempt to try to draw our way through this discussion. Let's see how the slides try to help us with this. So I'm going to go down past their general inverse function reminders, which we talked about, or I talked about in the last video. And then they finished by reminding us that the overall picture was you can reflect points across the diagonal line y equals x, and that ends up causing you to reflect an entire graph to get an inverse graph. And then they say, all right, now let's do this for the sine function, beginning on slide 9. All right, so if we have this notation now, we have y equals inverse sine of x, which I just drew too short. Or as I mentioned, you could also write this as arc sine of x, and that avoids using that little -1 notation that sometimes gets confused with an exponent when it's not. But what they just basically say right up front here without any descriptions of why or how it came to be this way is that what this means when you have y equals inverse sine of x is that x was the result of sine of y, where y is the angle and x was the answer you got. And specifically when y was between -π/2 and +π/2. So that's how they're expressing the restriction of which angles we can use. And you have to do that in order to get an inverse function. And they make a nice phrase for us here. Y is the number which is an angle in the interval between -π/2 and π/2 whose sine would give you x, or whose sine is x. And what does this wordology translate to? Again, like the example we did, if I have inverse sine of 1/2, then this would be the y value we're looking for. So that is the number or the angle between -π/2 whose sine is 1/2. So this is basically saying what angle theta makes sine theta equal 1/2. That's what this phrase is trying to have us wrap our minds around. And you would have to come up with the fact that to get 1/2, the angle is π/6 to be within this range and to get that angle. Now, the sine function itself will produce a 1/2 in infinitely many different places because it's periodic. It just keeps making 1/2 again and again and again and again. If we go back to the original sine function, which I had sketched here, just to sort of show 1/2 takes place like everywhere along here. There's a horizontal line at 1/2, and you have a point here at π/6, but the sine function will give you 1/2 at π/6 and over here, and again over here, and back over here, and over there. You can add 2π, you can get 5π/6, also gives you 1/2. There's infinitely many places where the sine function gives us 1/2. So an inverse doesn't exist if you consider all of those places, because there's infinitely many choices for the answer for the inverse function. It doesn't know what to do. So to get a function out of it, we have to throw away all those other possible places and just focus at the one between -π/2 and +π/2. And so that's what's going on in this restriction. And that's what the inverse or arc sine of x does. It says y is the angle measurement number in the interval between -π/2 to π/2 whose sine value would give you the x that you plugged into the inverse here. So they just sort of state that. It's hard to really wrap your mind around it. Now here's what the graph looks like on a snapshot from a Texas Instrument, I guess, or something like that. Doesn't look very pleasing or hard to use, but this basically does tell us that you could plug these things into a calculator and get a decimal approximation. So in this case, they plugged in x equals 1/2 or 0.5, and it gave us this sort of ugly number here. But as we were just seeing, if we're ourselves evaluating inverse sine or arc sine of 1/2, the answer we should get is exactly π/6. And that's because sine of π/6 gives you 1/2. So this would be the decimal approximation of π/6 that the calculator would give you if you typed into the calculator inverse sine of 1/2. All right, so we can look at another value. They just have another example. Let's say we wanted to evaluate the inverse sine of -1, get that y value. We would remind ourselves that the y answer has to be within the limited range of the possible angles we would consider. And then we would say, all right, well, where between negative pi over 2 and pi over 2 on a table of values or on a graph or from the angles that I know, which of those angle values would give me -1? And the extreme leftmost value would be the one where you get a -1. And so the angle we're looking for is negative pi over 2. And that's because sine of negative pi over 2 gives me -1. Since that's the angle that gives me -1 and it's in the range that I need it to be in, that's the answer for the inverse sine function. So this is a lot to get used to, but this is how the sine function inverse is defined. I think they have a nice summary page here. Let's see if that's next. No, not yet. They're going to have another example. All right, let's look at this example here. So then they're saying, all right, finding inverse sine functions continued, values continues. How about sine inverse of -2? So that means y is some angle so that sine of y equals -2. Well, when we try to think of an angle that would cause the sine function to be -2, we would hopefully quickly recognize that the sine function is never -2. That's outside the domain, the range possibilities of the sine function. Sine only gives you numbers between -1 and 1. So since that's outside the range of sine, that means it's not in the domain of sine inverse. So they sort of say -2 is not in the domain of the inverse sine function. The domain of the inverse sine function is just the answer sine could give you from -1 to 1. So that means that this expression's answer does not exist. Another way this is sometimes referred to is it's undefined. It's like trying to divide by 0. There's just no answer for that. And they point out that if you try to punch that on a graphing calculator, it will give you an error message. It'll just like E for error or something like that. So there is no sine inverse value for -2 because there's no angle you could put into the sine function that would make the sine function give you a -2. Since that angle doesn't exist, the answer to this expression does not exist. All right. So there's a caution box here. Let's see if we can make sense of it. Be certain that the number given for an inverse function value is in the range of the particular inverse function being considered. And so this is a caution based on the example they just showed us. Since -2 is not in the range of the sine function, then it cannot be evaluated in the inverse sine function when you plug it in. So let's just to show how we could take this concept and translate this into all the work we're about to do. We could then say, for example, note sine inverse of 5 does not exist because there's no angle that will cause the sine function to give you a 5. Sine inverse of pi. This might look like something you could evaluate because we plug pi into the sine function. Why can't we plug it into the inverse sine function? Looks like something you could do. But again, pi is not between -1 and 1. It's more than 1. It's like 3 point something, something, something. And so there's no angle you could plug into the sine function to get a result of pi. So again, this does not exist. And I could even, we haven't gotten to defining them clearly yet, but this principle would apply to other things. I could say, well, what is the cosine inverse of 7? Well, however the cosine inverse function works, it should be saying the result of this would be some theta where cosine of theta gives you 7. And cosine, like the sine function, never gives you values bigger than 1 or less than -1. So this as well does not exist. So that's what this caution is about. All right, so here's a nice inverse sine function summary. And so what they've done is they've taken some of our popular angle values here that we have been able to use on the sine function, but only the ones between negative pi over 2 and positive pi over 2. I think we are supposed to have a negative on this one here, which doesn't seem to be there for some reason. So we only have those sort of common angular values that might have been in the domain of the original sine function when restricted. Oops, sorry, phone's ringing. Hang on one sec. And what we can see then is that those might be the kind of answers you would get if you plugged the responses of the sine function into the inverse sine function. We basically just take these common values from the table of values for sine, and we flip the x and the y to get a table of values for inverse sine. They have a much better version of the graph than I produced, but they just show the end result. So again, you can imagine that the way this was obtained was they flipped that one restricted piece of the sine function across the line y equals x to get the graph that they're showing you here. And this then becomes what the picture looks like for the inverse sine function. Notice, unlike the inverse sine function, this is not periodic. This does not go on for all real numbers. This has a very limited domain and a very limited range, which are listed here. And the domain of the inverse function would have been the range of the sine function. And the range of the inverse function is the domain after we restricted it on the sine function, the restricted domain on the sine function. Questions, comments, discussions about any of this? So initially, the way we use the inverse sine function by hand, just to evaluate some valid number that's plugged into it, in which the answer exists instead of being does not exist, is we would kind of look up the input value for the inverse sine function onto this table of values here, or you could even use a sine table of values and look up the answers and then go back and see what the original angle input would have been to get that. And hopefully some of the more common ones have been remembered at this point or committed to memory. And like unfriendly values for the sine function that you can type on a calculator, unfriendly values for the inverse sine function can be typed on a calculator, and it'll give you a decimal approximation of the answer. But the answer will always be between negative pi over 2 and positive pi over 2 in decimal form on a calculator. All right, well, let's see if we can then see how this would move forward into all of the other inverse trig function graphs. So we've got a little less than 15 minutes left. Let's just take a look. They'll finish up with their properties, and then we'll extend that to the other trigonometric functions. So properties, you can see now that we're looking at this nice picture of the inverse sine function, and what it looks like is that it's increasing and continuous on its domain, which is from -1 to 1. It's going up and up in value all along the way. The x-intercept is 0 and the y-intercept is 0, just graphical properties when you're looking at a graph, not even knowing where it comes from, but just looking at the graph. And that the graph is symmetric with respect to the origin. So it points out the graph is symmetric with respect to the origin, and that algebraically means that if I change the sign of the angle, or I shouldn't say angle at this point because it's not an input, if I change the sign of the input and I put in a negative x instead of a positive x, that you get the opposite as if you had put in the positive angle x. We can see this on the table. If I put in a -1, I get negative pi over 2. If I switch that to a positive 1, I get positive pi over 2. And this was true about the sine function itself. The sine function is symmetric with respect to the origin, and so is the inverse sine function. All right, so then now moving on, how would we think about doing all these for the other functions? So let's just review with the time we have left, what this looks like when we do this to cosine and to tangent and things like that. So they say, all right, well, when we have the inverse cosine function, which can also be referred to as the arc cosine function, and you plug in an x into that, it means x was equal to cosine of the y value that you're looking for. And in this case, look at the restriction is between 0 and pi. So notice the domain for the inverse cosine function, the restricted values of what you can get. The restricted domain for cosine is not the same as the restricted domain for the sine function. They used a different restricted domain. So just to sort of try to sketch it real quick here, it'll look sloppy, but maybe it'll give you a visualization. If we consider the cosine function, which kind of looks like this, well, we want to get a piece of the cosine function that covers all values between 1 and -1. And so the piece that they used is they went between 0 and pi. That's how they restricted domain. And then they threw away all the stuff to the right of pi and all the stuff to the left of 0. And then they got a 1 all the way down to a -1 and all the values in between. So they restricted the domain of the cosine function to be between 0 and pi. And so now the answers you will get, the range values for inverse cosine, will only be angles between 0 and pi. This is what that flipped function looks like. Again, they'll do a better picture in a second when they do a summary. But if we were trying to evaluate the inverse or arc cosine of 1, you would basically be asking yourself which angle between 0 and pi would cause cosine of that angle to equal 1. And we can remember in this range that cosine of 0 is equal to 1. And so they would say, since cosine of 0 is equal to 1, then the answer for arc cosine of 1 is 0. And you could make a table of values, and you can imagine you plug in your x's, and you're getting the inverse cosine. And so this would tell us, well, if I plug in a 1 to the inverse cosine, I get a 0. And you could fill out a table of values, or you could just flip the input angles between 0 and pi on the cosine table of values. And if you flip the x's and y's, you get cosine inverse tables of values. Similarly, if I'm trying to evaluate the inverse cosine of -√2/2, I would say which angle in this range would cause the cosine to equal -2/2, -√2/2. And so in that range, that happens when you're at -3π/4. I'm sorry, not negative, just at 3π/4. That's between 0 and pi. And looking at this little restricted chunk here, you're sort of talking about down here somewhere, or on the graph, you could say, all right, well, that's going to happen at 3π/4 when I'm stuck between 0 and pi, and so that's the answer for the inverse cosine. So there's this nicer summary here. You could imagine common output answers of the cosine function, -1, -√2/2. You could do 1/2, -1/2. Those common values, then you would say, here are the angles that are between 0 and pi that would produce those answers in the cosine. And so therefore, those are the answers for the inverse cosine. And if I flip that little piece of the graph across the line y = x, I get this nice picture of what the inverse cosine graph looks like. Again, this is not periodic. You can't plug in any real number you want. You can only plug in values between -1 and 1. Those are the domain values, which they list up here. And the answers you get will always be between 0 and pi based on the restricted answers for the cosine function. All right, so notice we have a different range now. We have the same domain because the output values of sine from -1 to 1 are the same output values of cosine, -1 to 1. But the range is different. The angles we're using to get those answers are different. For inverse sine, it's negative pi over 2 to positive pi over 2. And for inverse cosine, it's 0 to pi. Now things get interesting. I'm going to skip over the properties here and look at the tangent as time is getting tight. Things get interesting when we get to the tangent. So we could begin by thinking about how we could flip some tables of values and take answers from tangent and map back to the angles that produce those. But the thing I want to point out that's very interesting right away is look at the domain. The domain is all real numbers. Now we don't seem to have this big restricted domain. And so how is it that this occurred? Let's maybe use some blank space over here. The thing to remember is that the tangent function looks kind of like this. It's periodic, but it has all of these asymptotes. Going back to our graphs. And that we go from negative pi over 2 to positive pi over 2 are the vertical asymptotes, and then we have like that, 3 pi over 2, etc. So in order to look at this graph with the idea of creating an inverse, we see again, well, it fails the horizontal line test miserably because horizontal line tests cross it tons of times. So that's not helpful. So when we choose to restrict that, what they did is they said, all right, well, in this case, however, we're not getting answers between -1 and 1. The tan function is giving us answers from -infinity all the way to positive infinity. And we can get all of those answers by restricting to pi over 2 and negative pi over 2. Then we get the tan function gets all answers from -infinity to positive infinity. So they throw away all these multiple repetitions of the graph. They restrict the domain from negative pi over 2 to pi over 2, which is the same restriction we made on the sine function. But when they do that on the tan function, they then flip it. They get a graph that looks like the middle graph here. And notice that it goes all the way to the right off to infinity and all the way to the left off to -infinity. But the up and down restriction is now between negative pi over 2 and positive pi over 2, just like the inverse sine function is. So the inverse tangent function, you can plug in any number you want into the inverse tangent function. And there will be some angle between negative pi over 2 and pi over 2 that would give you that result. You can plug in a 1, a 5, a million, a billion, -77. You can plug in anything you want. And there's some angle in the, and the inverse tangent function will produce that angle that's between negative pi over 2 and pi over 2 that would give you that result. Okay. So properties of the inverse tangent function, they'll point out that we now have a domain that goes from -infinity to positive infinity. It has an x and a y-intercept of 0. The lines pi over 2 and negative pi over 2 are horizontal asymptotes. So now what happened is when we had vertical asymptotes in the original graph, and we flip or reflect the original graph around the line y equals x, well, then those vertical asymptotes get flipped and they become these horizontal asymptotes. So this is the line y equals pi over 2 is that upper dotted line. And so that as x gets bigger and bigger and bigger in the inverse tan function, the answer for the angle gets closer and closer to pi over 2. And so the function approaches that as a horizontal asymptote. Anyway, so they have the properties here. We also have that this is symmetric with respect to the origin, just like the tan function is. And with the last couple of minutes left, let's take a look. We could also have the inverse of the cotangent function, where they have, again, you can plug anything you want into the cotangent function. The domain is -infinity to infinity. But now, like the cosine function, the restricted domain on the cotangent function was 0 to pi. And so the range will be 0 to pi. So the range of cotangent is inverse cotangent is like the range of inverse cosine, and the range of inverse tangent is like the range of tangent of inverse sine. And so this will help us to sort of keep in mind what's going on here a little bit. And then we can also do the same thing for secant and cosecant. Now this is going to start to look a little bit more confusing because unfortunately now our graph is in a couple of pieces. We have to really look at the range that they're using here. So again, just to imagine how this could have happened. The secant function is the flip of, or arcsecant is the flip of the cosine. And so with the cosine function, they use just this part of the cosine function. Well, let's see, let's do it this way. Here's the cosine function. And so the secant function would have been these values. And they also would have been up here. And those shouldn't cross. There should be a line going between the two. So they just took this piece and this piece when they restricted the domain, and when they flipped them, they got the piece on the left. Oh, that looks terrible. I'm just going to erase it and forget that I ever did it. In any event, you can look at the secant graph and imagine the part that they took between 0 and pi only, and then they reflected that around the line y equals x, and they get these two different pieces here. And this makes the domain a little confusing. It makes the range very important to think about how they got that. And they do the same thing for cosecant, and they get another two pieces as well. And that's going to be the inverse for all 6 trigonometric functions. Let's just finish off on the slideshow by looking at this table. This table gives a nice summary of the domain of each of these, the interval of answers, the range interval that you would get, and which quadrants they would be in terms of thinking about which angle you would choose from. So this is a really good summary when you're trying to wrap your minds around this to reflect back to in the future. And that's where we will finish today as time is out. I will try to shoot another video to continue into some of the examples they have later of a particular kind, but for now the time is up.